Thank you, Mr. Chairman, for the kind introduction. At first, I would like to start with an overview of my talk. So I want to begin with the introduction of the material and its microstructure we are investigating. Afterwards, I come to the explanation of our experimental setups we are using. And in the middle section, I want to show you our recent results regarding the evolution of fatigue damage, and at least I want to sum up my talk. So the material we are investigating is low alloy carbon steel. The German designation is 50 chromium molybdenum 4, and typically this kind of materials are quenched and tempered, and so is our material to medium hardness of 37 Rockwell, which gives an ultimate tensile strength of 1178 megapascal and an ultimate strain of nearly 14%. So the material is fully martensitic, and this chaotical microstructure is following a strict hierarchical setup made out of rare austenite grains, packets, blocks, and martensitic glasses. And so one pure austenite grain consists of several packets which are made out of blocks with all the same 111 plane in the austenite, and these blocks contain the martensitic glasses and the different kind of variants, which is important to discuss the material's behavior until fatigue loading. So the test setups we are using is on one hand resonance testing machine from the company Umul, which allows 400 Hertz testing frequency and 100 kilonewton. And the other machine, I think, which is well known, is the ultrasonic fatigue testing machine from the Boko Vienna. And in both cases we are using cylindrically bulk specimens, which are electrolytically polished. Both kind of specimens have one in common. They have both a small shallow notch in the middle section of the gauge length, which produces a notch factor of 1.2, that we have a slight stress localization but not affecting the natural fatigue mechanism. Our focus related to fatigue is on the fatigue damage detection on the surface during the fatigue test. So therefore, high resolution thermography, digital light microscope, or an integration of our ultrasonic fatigue machine into a high resolution scanning electron microscope is possible. So at first I would like to show you the SN diagram, what we got from the material under fully reversed loading under laboratory air atmosphere. And it is obvious that we have a strong frequency influence, which can be attributed to a kind of strain rate effect. But additionally, for both cases, if we have fatigue crack initiation or if we have fracture, we only observe fracture at the surface of the specimens, and we could not observe any fracture above 10 to the power 7 cycles. But I have to mention that we investigated the specimens afterwards the test, especially the runout specimen, and what we see is a so-called surface roughness, and we relate this to an effective plastic strain amplitude, which leads to somehow fatigue damage. And we think that the effective plastic strain amplitude is really low and not measurable on a macroscopic scale, but somehow maybe on a microscopic scale, and therefore we start with a detection of local plastic deformation by high resolution thermography. We are using therefore a thermographic camera from the brand Infratec from Germany, and this picture here shows the magnification. So this is 2.6 millimeters, and 3.2 millimeters, which results in a resolution of 5 micron for 1 pixel. And this camera is adapted to the Rumel Testronic machine. So the first test we conducted were a so-called load increase test, just to treat the material and have a look what's happening, what can we observe on the surface of the specimen. So we are starting our load increase tests at a stress amplitude where the material behaves purely elastic, and then we are increasing the stress amplitude after every 100,000 cycles for 6 megapascal. And for a kind of feedback signal, we choose on one hand the blue curve here, which represents the change of resonance frequency, and on the other hand, the red line represents the change of temperature measured by the thermography camera. So what we see here is that the first change in resonance frequency can only be observed after 2.2 million cycles, and we correlate this with the macroscopic crack initiation and fatigue crack growth. But on the regarding temperature change, we see a much more sensitive feedback signal, and I want to show you a small video. Hopefully it's working out. So after 600,000 cycles, we see this lift off of the temperature. And this lift-off here can be correlated with a first start of so-called hotspots. So what we see is in the microstructure, we see the development of local plastic deformation, and the corresponding stress value, what we have here, corresponds well with the cyclic yield strength, what we have obtained by incremental step tests. This ongoing temperature change correlates then with the intensifying process of this local plastic deformation, and leads then to the end of the lifetime of the specimen to a fatigue crack initiation and crack growth. What is interesting is that the local plastic deformation is located in these zones. And first we thought about something like a surface effect. So we were interested in what's really going on. We conducted element mapping along the fatigue crack growth front, and we see that the chromium content is alternating. So we have areas with a surface roughness, so with local plastic deformation, and in these areas we have less chromium, which leads to a microstructure where we have coarse martensitic microstructure and less pronounced chromium carbides. And on the other hand, where we have enough chromium, we see a much more finer martensitic microstructure and more pronounced precipitation of fine chromium carbides. And additionally, we also conducted micro-hardness measurements, and I guess this value here in comparison to this value gives a good explanation why we have concentration of local plastic deformation in these areas. Now I want to show you two examples for runout specimens. The first example is a specimen which has been loaded up to 2 times 10 to the power of 8 cycles with a testing frequency of 95 Hz. And yeah, the first thing what we can obviously see is that this aluminium-based inclusion does not affect anyhow the fatigue life, but in the surrounding area we can observe again this surface roughness. And if we have a closer look, we can see it's almost looking like a small crack which is already open against the surface. To clarify what is going on beneath the surface, we conducted some film cutting in this section here, and we see we relate this shadow here to an ongoing fatigue crack initiation stage. You also can see here a small void. Yeah. In comparison to the frequency of 95 Hz, we also see the same events at the high frequency, and we obtained in this case here the crystallographic orientation of the microstructure by VHCF measurements. I painted here the events corresponding into this block here, and by reconstruction of the martensitic microstructure, we can clearly see that this event is parallel to the 111 direction in Osnet, or parallel to the 110 plane, in the ferrite. To clarify again the question, what is beneath the surface, we did again a flip cutting, and again we see this events beneath the surface, and we would declare this as an ongoing stage of fatigue crack initiation, a transgranular crack initiation caused by cyclic visibility. And we would say that we have fatigue crack initiation in the very high cycle fatigue regime, but that the surrounding microstructure acts as an effective barrier against fatigue crack propagation. So let me sum up my talk. What we can observe is that we have a pronounced frequency influence on our martensitic material. The detection of local plastic deformation by thermography was shown, and this is possible. The cyclic yield limit could be obtained by a load increase test and also by incremental step tests. The influence of microstructural banding was also shown by the thermography, and crack initiation was found even at the high number of cycles, but the surrounding microstructure acts as an effective barrier against fatigue crack propagation in the very high cycle fatigue regime. And at least I have to thank you for your attention, and if you have any questions, feel free to ask. Thank you.